This is a short tutorial to introduce the concepts of acids and bases. The first question we can ask ourselves is, how do we identify which compounds are going to act as acids? Well, we have some characteristics of acids that we'll identify here. The first is acids react with what are referred to as active metals. What are active metals? Well, active metals include group 1 elements, lithium, sodium, potassium, are metals that react with acids or even water, which can be classified as a weak acid in some cases. These elements oxidize during this reaction with acids and produce hydrogen gas. Group 2 elements, beryllium, magnesium, calcium, are metals that are reactive enough to react with acids, but not reactive enough to react with water, and similarly oxidize in their reaction with acids to produce hydrogen gas. Acids are materials that will react with carbonates to produce carbon dioxide, so you can react acids with things like limestone, which is mostly calcium carbonate. Also, acids will react with bases to produce salts. If we want to go into our kitchen and think about a common household acid like vinegar, if we taste vinegar, it tastes sour. Of course, because of safety considerations, we never test lab chemicals and are not recommending that here. In biological systems, we find acids in places like our stomach, as a for instance. Our stomach has a small concentration of hydrochloric acid, which functions in two ways. One, it starts to pre-digest our food and also acts as an environmental barrier to most bacteria that we would ingest in our food to keep those bacteria from progressing through our digestive system. Biological systems have evolved ways to handle these acids with linings in the stomach, as a for instance, that resist reactions with acids. Again, common household acid, the one we always think about first, is vinegar, whose real name is acetic acid. Also in the kitchen, we'll find the salts of acid-base reactions, things like bicarbonate, which we see in baking soda, or even a material called baking powder, which is actually a mixture of a solid acid and a solid base, and they do not start reacting until we add water. Well, we're going to address three different definitions of acids and bases in this talk. The first one we're going to talk about is the Arrhenius definition. The Arrhenius acid definition is the simplest. An Arrhenius acid is one that ionizes when mixed with water to produce hydrogen ion. So typically when we write HCl dissociating into hydrogen ion and chloride ion, we write it like this. But there's actually, we're producing hydronium ion, H3O plus, not hydrogen ion. And the reaction that's happening in our beaker actually looks like this, where the HCl is reacting with water. Water is accepting that hydrogen ion to form a hydronium ion, and then chloride. There's no such thing as H plus in water. But we're all very lazy, including chemistry professors, and we often write H plus when we actually mean hydronium. The Arrhenius definition of base is a compound that ionizes when mixed with water to produce hydroxide. So if we take sodium hydroxide, put it in a water solution, we will get sodium ions and hydroxide ions, making sodium hydroxide an Arrhenius base. Acids and bases react in neutralization reactions. So if I take a solution of sodium hydroxide and react that with a solution of hydrochloric acid, I will get sodium chloride, a salt, plus water as the result of that reaction. Looping back around on previous topics, I challenge you to write that last acid-base reaction as a net ionic reaction. Well, common acids that we find industrial in the environment and sometimes in our own households have different classifications. The first classification of acids are acids that are called oxyacids. As you can see, for each one of the oxyacids designated here, we have oxygen involved in a complex polyatomic anion, and that polyatomic anion, when protonated, having a hydrogen ion on it, gives us our acid. We also have examples of binary acids where we only have two atoms involved. We have a hydrogen and a halide in the two examples here, hydrochloric acid or hydrofluoric acid. Acids can also release more than one hydrogen ion in an acid-base reaction. A sulfuric acid is an example of an acid which is polyprotic, poly meaning more than one, protic referring to the proton that will be released during the acid-base reaction. Phosphoric acid, carbonic acid, and boric acid are also examples of acids that are polyprotic, and for every mole of acid we put into a system, we will get more than 1 mole of hydrogen ion. Well, what properties do bases have? Well, the first one is kind of a circular definition. Bases react with acids to form a salt in water. Sometimes these bases are referred to as alkali compounds. Many of them are a result of reactions to produce either group 1 alkali metal hydroxides or group 2 alkali earth hydroxides. So they're often referred to as alkali compounds. If you accidentally get some on your skin, they will feel slippery, and actually that brings up a safety issue. In many cases, bases can be more dangerous than acids. It takes longer for you to get a sensory feeling that you're burning, and those bases then have a chance to penetrate your skin farther deeper than acids do before you realize you actually have a problem. As we said, bases react with acids to produce salts, and also hopefully we know or instinctually know that those acid-base reactions often produce a lot of heat. In the laboratory, we have to be very careful if we're adding acids and bases together, because these reactions are exothermic. And of course, exothermic means that the reaction is releasing stored energy to the surrounding environment. Well, if a reaction produces a lot of heat and exothermic, what does that tell us about the stability of the reactants that we put together for that reaction? Well, what it tells us is there is a lot of energy stored in acids and bases, and when we react those together in a neutralization reaction, all of that stored chemical energy is released, and we need to be very careful in the laboratory that we're capable of handling that energy release. While your stomach has acid, once your food passes through your stomach into your intestines are actually basic. So our biological systems have evolved to expose our food first to acid to start the digestive process, and then to bases to continue that digestive process. What kind of common household bases are we talking about? Well, sodium bicarbonate is baking soda, and it is a common base. Most drain cleaners that you would use, think liquid plumber, are either sodium hydroxide or potassium hydroxide. And there are many ammonia-based household cleaners where ammonia is the base that we're using, that are good for cleaning up greasy films. Ammonia is great for reacting with bio-based oils. Common bases we'll see here, again, hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, kind of the list goes on. Ammonium hydroxide on the last entry is actually the compound that you get when you mix ammonia with water. Ammonia reacts with water, removing a hydrogen from a water molecule, producing an ammonium +1 ion and a hydroxide -1 ion. Well, the next acid-base definition we'll look at will be the Bronsted-Lowry definition, which is broader than the one that we've already looked at, and as a result of being broader, also includes all of the Arrhenius acids and all of the Arrhenius bases. So the Bronsted-Lowry definition is broader than the one that we just looked at for the Arrhenius definitions. Now acids are defined as compounds that donate a hydrogen ion during reaction. Bases are defined as compounds that accept a hydrogen ion during reactions. You'll notice that water and hydroxide are no longer parts of these definitions. Well, if we take a look at an acid-base reaction like the one shown here between carbonic acid and water, the first thing that we want to consider is every time we look at an acid-base equilibrium like this, both sides of the reaction include an acid and a base. So every acid-base equilibrium has two acids, one on the left-hand side, one on the right-hand side, and two bases, one on the left-hand side, one on the right-hand side. Carbonic acid on the left-hand side produces, as the result of this acid-base reaction, a conjugate base, which is bicarbonate. Water on the left-hand side, which is acting as a base, produces hydronium ion, a conjugate acid, as a result of the acid-base reaction. You can see that we no longer need to have water or hydroxide as these definitions. We don't have to run these reactions purely in aqueous solutions. We can choose to run them in a different solvent. An interesting example of these definitions can be found by looking at amino acids. The one shown here is alanine. And if we take a look at amino acids, what we find is there is one functional group in this organic molecule which will act like an acid and give up a hydrogen ion during an acid-base reaction. We have another part of the molecule that in this case contains a nitrogen functional group which is an amine related to ammonia that can act as a base by accepting a hydrogen ion. And if we look at these molecules, we can see once they're in solution, we can get an internal acid-base reaction where our carboxylic acid shown on the left ends up forming the conjugate base carbonate on the right-hand side of the reaction. On the left-hand side of the reaction, our base accepts that hydrogen ion released by the carboxylic acid to form an ammonium functional group with a positive charge. Here's an interesting vocabulary word. When we have internal charge separations in a molecule, where one part of the molecule is negatively charged, one part of the molecule is positively charged, we refer to those as Zwitter ions. Finally, we're going to take a look at a third definition of acids bases. We're going to talk about Lewis acids and Lewis bases. And again, this is a broader definition that includes everything we've defined either as an Arrhenius or a Bronsted-Lowry acid and base. So our definition part 3 for Lewis acids is an acid is a molecule that accepts an electron pair during a reaction. A base donates an electron pair during a reaction. So if we take a look at a hydrogen ion reacting with a water molecule to give us a hydronium ion, we can clearly see that the hydrogen ion with a positive charge will act as the electron pair acceptor, accepting an electron pair, 2 electrons from the oxygen and water. Water will be the electron pair donator. 2 of the non-bonding electron pairs in water will be used to form that bond with our hydrogen ion. So this still looks like an Arrhenius or Bronsted-Lowry acid-base reaction. Let's look at one that shows the full range of Lewis acid and base definitions. Let's look at a molecule like aluminum chloride. If we go ahead and draw the Lewis structure for aluminum chloride, we'll get something that looks like this. And if we want to draw that molecule three-dimensionally using the skills that we've acquired as we've translated Lewis structures into three-dimensional shapes, we find that aluminum trichloride is a trigonal planar molecule. We have three repelling electron groups. But we need to acknowledge that even though it is empty, that aluminum did have one more p orbital that's unreacted. So although it's empty, that aluminum still has an extra p orbital. Aluminum chloride is capable of reacting with molecules like ammonia, where one of the atoms in ammonia has an extra non-bonding electron pair. Aluminum won't form a fourth bond because it's out of valence electrons, but it is willing to accept both those electrons from another molecule that has a non-bonding electron pair to insert into that orbital. So now we see our definition of Lewis acid. Aluminum trichloride, which has no hydrogens or hydroxides, is acting as a Lewis acid by accepting an electron pair. Ammonia is acting as a Lewis base, not because it's reacting with a hydrogen ion, but because it's donating an electron pair during this reaction. We end up with a molecule that looks like this, and you'll notice, looping all the way back to our discussion of three-dimensional structures, aluminum trichloride now has changed from trigonal planar to tetrahedral because it now has four repelling electron groups around the central atom.